Curious observant. Almost every morning begins with a look into a flat piece of glass. You stand in front of it, and a perfectly scaled, virtual version of yourself stares back. But the reflection you see is flipped. If you raise your right hand, your counterpart raises their left. This is lateral inversion, a geometric reversal where the right side of a physical object is reflected as the left side. Your reflection also appears to exist in a space distinctly behind the glass. If you stand 2 feet away, the image seems to stand 2 feet inside the wall, creating a convincing illusion of physical depth. This everyday illusion is entirely predictable. It happens because light follows a strict, unbending set of physical laws every time it hits a surface. To understand those laws, we have to look at Fermat's principle. Proposed by a 17th century mathematician, it states that light operates as a strict optimizer. It will always take the fastest possible path to its destination. Think of a bird dropping down to grab a seed on the ground before flying up to a second branch. To minimize its time in the open, the bird naturally selects the shortest geometric route. Light does the exact same thing. Because light always selects the path of least time, it follows the core law of reflection. When a light ray strikes a surface, the angle it arrives at, the angle of incidence, must exactly equal the angle it bounces away at, the angle of reflection. On a flat mirror, every imaginary perpendicular line pointing out from the glass is perfectly parallel to the others. These are called normal lines. Because the normal lines are parallel, incoming light bounces off evenly, preserving the exact scale and proportion of the original object. But if flat glass perfectly preserves the image, what happens to those straight, parallel paths when we physically warp the shape of the surface? Let's take that flat, reflective surface and physically bend it inward, shaped like a bowl. This creates a concave shape. Because the surface is curved, the normal lines are no longer parallel. They point toward each other. When parallel light rays hit this bowl, they are forced to bounce inward and intersect at one specific location. We call this the focal point, and the process is known as convergence. As the light rays cross over one another at that focal point, the top rays become the bottom rays, and the bottom rays become the top. This projects a real image, an actual physical projection of light that is now visibly upside down. Forcing all that light to a single intersection creates a massive concentration of energy. According to historical accounts, the Greek mathematician Archimedes used this parabolic geometry to converge sunlight onto invading Roman ships, setting them on fire. We apply that exact same geometry today. By positioning a pan precisely at the focal point of a highly reflective concave dish, you can capture enough concentrated thermal energy to boil water or cook a meal entirely without fire. On a much smaller scale, doctors use tiny concave mirrors. By placing a tooth closer to the mirror than its focal point, the diverging rays create an upright, highly magnified image of a very small area. By forcing light to bend inward and weaponizing the focal point, concave mirrors take light from a simple virtual illusion and turn it into a tangible physical tool. Now let's reverse the physical manipulation. If we bend the reflective surface outward into a dome, we create a convex shape. The normal lines on a convex surface splay outward. When parallel incoming light strikes the dome, the rays are forced away from one another, scattering in all directions. This is called divergence. Because the reflected rays never actually cross, they can't project a real image. Instead, your brain traces those scattered rays backward through the glass, creating a virtual image that appears shrunken and upright. This creates a direct optical trade-off. By geometrically shrinking the physical size of the objects in the reflection, the mirror can pack a dramatically wider area into the same piece of glass. We rely on this expanded field of view every time we drive. The convex shape of a passenger side mirror gathers light from a massive swath of the adjacent lane, revealing vehicles hiding in blind spots. Convex mirrors deliberately sacrifice precise visual scale. They trade precise size for a massive expansion of our spatial awareness. Every distorted reflection we encounter in our daily lives is simply geometry manipulating light's strict adherence to the fastest possible route. When you scale up a concave curve, it becomes a massive net. A satellite dish operates on the exact same geometry as a solar cooker. catching invisible radio waves and bouncing them perfectly into a central receiver. At the architectural level, an entire building faced with curved mirrors can capture enough solar convergence to generate extreme temperatures required for industrial research. These massive energy gatherers contrast with the daily, life-saving utility of a simple convex curve, keeping drivers safe on a crowded highway. From our simple bathroom mirrors to massive satellite arrays, the geometry of the surface strictly dictates the destination of the light. By altering that shape, we transform a simple physical law into a precise technological tool.